for record all students are in the class. Okay, let me know if you're not able to see anything on your screen. So we have covered one of the example just now. We now look at a pump performance. So how do we characterize pump performance? So this is also in your lab 2 and lab 3. So in your report, you'll cover about this one. So on your screen or in your handouts, question 7, you'll see a normal pump setup. So meaning there's a pump and from 1 go in and then go out point number 2. If you look at the gauge arrow, from point 1 to point 2, the pressure increase. The arrow pointing this way and the arrow pointing that way. All right, so pressure increase with clockwise rotation of the arrow. So you can see when the water come from 1, after it go inside the impeller or pump, the water pressure will increase. Then we have valve. We have a valve here to allow the flow to continue to flow. And we put a flow meter there, a flow meter after the valve. So we measure the flow meter Q value here. So, and then the elevation between point 1 and point 2 was given. Z2 minus Z1 is the elevation. So every time you study about fluid mechanics or about fluid, when you see about elevation parameter was mentioned, it means that you need to call out the energy equation, right, or Bernoulli equation, right? So this is the equation we use for calculating the actual head race. HA equal to this one, all right? And then simplification steps was applied to this equation. The first one, we take out the Z2 minus Z1, because usually the differences of the elevation usually very small. Okay, so we can take out to calculate the actual head race. We use this equation, but we can cancel out the difference of your elevation, because in an actual scenario, the elevation may the value is very small, right? The value is very small, and the velocity also, right? The velocity, the differences between 1 and 2 also a bit different. Only different is the pressure. Okay, only different is the pressure component. Velocity normally, when you have a pump, velocity usually is almost same. In and out also same, but it's only the pressure will change a little bit. Okay. So your actual head race equation will arrive with this near to sign, with the wave sign, HA, actual head race, near to the difference of your pressure divided by specific weight, and the power transfer to fluid given by this equation. Power equal to your specific weight times the Q times the HA. So from here we can write we can write the equation further. Sometimes we can the textbook that I'm using, they are defining using horsepower. Horsepower, we know that is an imperial unit, but you cannot avoid this horsepower term when you go to industry, because some of the machine you buy from United States, you buy from Germany. So sometimes the industry people, they use horsepower to define the pump. Okay, so sometimes when you design about pump, you calculate a few kilowatt, a few thousand kilowatt, but sometimes when you go to the market to buy pump, they are not labeled as you calculated. They will give you in terms of horsepower. So what you do is that they will take this the ratio divided by 550, then you get your answer. The top one is in watt. You take the specific weight Q times the HA, you get in watt, WATT. But you want to convert in horsepower, you divide by 550. Then you'll get in this one. This is a side note now. This one, when you want to use the 550, right? When you want to use the ratio to convert in horsepower by 550, all your unit must be in imperial unit. So like the specific weight in pound per feet square, Q in the feet cube over second, and then your actual head race is in feet. So just be careful when you go to industry. When you do conversion, you need to be careful, right? When you use 550 means all the parameter here you use the unit. Normal calculation, unit SI is this equation, and power, the unit for power always end up in a watt. And efficiency, the concept always we take what is your output divided what is your input. Okay, output divided by input. So in a pump, what is your output? Is a power gained by the fluid. So it means that the receiver, what is the benefit by the receiver? The receiver is a fluid. So the power gained by the fluid is the output. What is your input? Input is from the shaft. The pump is using shaft power. So the shaft power converted the energy to the fluid. So output divided by input, or in mathematic form, you take the PF, which is the power gained by the fluid. F represent the fluid, and the shaft power, W, capital W dot shaft. Okay. Yeah. And sometimes in the pump specification also give you the brake horsepower, BHP, right? BHP, right? Okay. So another again, just to remind you that every time you use horsepower, all the unit that you use, the specific weight Q and HA is in the imperial unit. Okay, so this is the form when you use the brake horsepower efficiency. So on the top, this one is a general equation that can help you to calculate in the normal unit SI watt, not watt. Efficiency don't have the unit. It's just a ratio between output and input. But if you want to use a horsepower unit, then you use this equation. And mathematic model used to calculate the overall efficiency is the product of three scenarios. We consider hydraulic efficiency, we consider mechanical efficiency, and we consider volumetric efficiency. Hydraulic, mechanical, and volumetric efficiency. Okay, all this also you can find in the specification of the pump. Okay, hydraulic, mechanical, and volumetric. So you're going to look at efficiency now. All right. Now this is the typical pump efficiency graph, which is on the left-hand side, you will have efficiency, horsepower, and head. And then the horizontal were given by Q. So you have on the left axis, since you have three, means that you have three lines. So one line is efficiency, one line is the head, one line is the brake horsepower. All right. And this is the efficiency. On this graph, on the graph that you see on the screen now, with the head, brake horsepower, efficiency axis versus flow rate, the most important lines will be the efficiency, because we want to look at what is the optimum efficiency of the pump that we buy. The efficiency, because you can see as we increase the flow rate, the efficiency will go up, go up, go up, go up until a certain point it will drop. Okay, even you increase your flow rate, all right, your flow rate. So the first point you look at the graph is that you look for efficiency line, go to the optimum point, drag, you get the optimum flow rate to get the optimum efficiency, and then you extend up, you'll get the brake horsepower at the optimum efficiency, and then you extend up, you'll get the optimum value of your head, but if you're using a certain pump. Okay. Again, I repeat, how do you use this graph in the industry? When you want to buy a pump, you look at a pump efficiency graph. Usually give you pump head, brake horsepower, and efficiency on the left, combined in one graph versus flow rate. How you read the graph or how you make full use of the graph. First is look at efficiency line. Then you go look at the top or the peak value of the efficiency. Then from the efficiency, you drop down. You get the maximum flow rate from the pump. Then you extend up, you get the brake horsepower. Then you extend up, you get the head from the pump. Okay. Right. Now another curve you'll see when you pump is three-dimensional or three axis graph. Oh, the one on the left is in head. Of course, this example is in imperial unit feet. Bottom one horizontal is in capacity, gallon per minute, gallon. Or if you convert to unit SI, gallon means there's an equivalent value for liter, right? Liter per minute. Gallon is in a unit imperial. Then on the right hand side is NPSH. Later we'll look at what is NPSH and why we need to study NPSH for pump. All right, so this is the graph. So yeah, later we'll look at this one. Okay. Now NPSH, positive suction head value. Why? Because in a pump, one problem that we try to avoid is called cavitation. Cavitation. This word seems like very bombastic word, or in the layman term, it means that sometimes your pump will create energy to the when you push the water, or it will increase the pressure, your water will evaporate. You'll create bubble. You'll see water bubble accumulate in the pump or in the pipe, which will make the efficiency drop sometimes. So cavitational is a scenario that we have tried to avoid at all costs in the industry, which means water bubble or bubble in the pipe or in the pump. Okay, cavitational, it just simply means your liquid pressure reach a certain location, certain value where the vapor pressure is generated. Vapor pressure means the state of your liquid change into vapor, right? Means you start to have a gas phase, right? So you imagine if you work in the oil and gas company, and you need to design a pump to pump the liquid gas from one station to another station. So you need to look at the pump. You need to look at a pump efficiency graph, and then you try to design according to the value of the graph on the graph, so that you try to avoid cavitation. Okay. So it's given by this equation. Right, again, this is the energy equation. So net positive suction head, or NPSH, is a very popular parameter when it comes to pump. When it comes to pump, it's very popular. You mention NPSH to any supplier of the pump, they will know. This value is very important because all the end user, they try to avoid the certain value because of the cavitation problem. So given by this equation. All right. The rest you can read from my slides. Okay. There are two value of NPSH. One is called required. One is available. Required and available. With a small denotation, R stands for required, and available means we will use the A. Okay. Required NPSH is an important value so that cavitation cannot happen. This value must maintain so that cavitation problem do not occur. Okay. NPSH. This value must be maintained so that cavitation do not happen. So sometimes I want to test your understanding about NPSH value. So I give you a value, and then if the value is less than the required value, for example, NPSH is 3 meter, and I give you the value that you measure or you get from experiment is maybe only 1 meter, then cavitation will happen. Okay. Right. So available means what actually happened. So for proper pump operation, NPSHA or available value must be more than the required. So again, this is also important when we try to test your understanding. What is NPSH value? Okay, explain why that value cannot use, or explain why a certain value is reasonable, or how you improve, and then you need to suggest how to improve that one. Okay, so this will be the format when it comes to online exam or open book exam. Okay. Again, remember, your available value must more than your required so that cavitation cannot happen. Yeah, and the problem of cavitation, what is cavitation, you must understand. Okay, I already explained what is cavitation. And there's a calculation for these two values, right? So you just look at the slide and at least you know that there's an equation for required and available NPSH. Okay. The rest you can read from my slides. And there's an example. There's a tutorial question about this one, NPSH. All right. So it's a very lengthy slides. I want you to go through. Right. I won't go through this one. I want you to go through. This one you read. NPSH. This one is your tutorial question number 10. All the steps, step by step, already give you in the PowerPoint slides. I want you to go and read. Go and read about this one. Okay. There are lots of steps given. Another one is called, and another section we're going to look at is that the system characteristic, pump system matching and selection. How are we going to select a pump? If you're given a certain graph, how you select a pump? Okay. Now, for example, we give you a scenario. Want to transfer water from point 1 or section 1 into section 2. So we use a pump to pump water into tank number 2, which is higher than your tank number 1. So we pump water from here, go into here. Or sometimes we will test your understanding. We will inverted the whole flow, means from high ground into low ground. Okay, so we have a Z1 and Z2. So this diagram is inside your hands up question 11. You can look at it. All right. So there's an equation to calculate the actual head. All right. And friction loss and all this. So all these parameters you should already be familiar. one equation is that in pump, there's one specific line, we call it system equation. Inside the when we want to select a pump, so we need to have a equation so that we know that our design can fit into the operation. So one of the equation is this one. We use a system equation to estimate the characteristic of our pump. So we use our HA equal to Z2 minus Z1 plus KQ2 Q square. K is a constant value. Is your KL value or your minor loss coefficient. K is a KL or your minor loss coefficient. Q is the flow rate. Z2, Z1 is elevation. So this is the system shown. So for example, in this case, you can calculate all the KL, or KL is given, right? Or Q is given. So Z1, Z2 is given. So you can calculate the HA for the system, right? So this is the equation we use to calculate HA. Then we can plot the system curve. We call it system curve. Why the name is system curve? Because we use a system equation. So the system equation is from the graph. You can see the relationship between HA and the Q. This is the quadratic equation. Y equal to mx square, ax square plus b is a quadratic equation. So you'll get a graph like that. Okay, you get a quadratic graph. Start with the intersection at Z2 minus Z1 and the quadratic curve here, because you have a Q square here. Okay, Q square here. All right, so you get a quadratic curve. So this is called system curve. So sometimes we'll ask you to plot this or choose the correct system curve. All right, so you use this equation to look at the system. All right, now this is under your hands up question 12. There's a diagram. There's a diagram. So there's a SOP or standard operating procedure. Okay, I'm going to brief you slowly. So usually you have a graph. You build a graph. You have actual head on the left, HA, versus flow rate Q, and then on the right hand side you have the efficiency. So you have an actual head, you have an efficiency. So by default, you will always start. How do you choose a pump? Okay, you have three axes. So you have HA, you have Q, you have efficiency. So I'll use this symbol, efficiency. So on the graph, HA versus Q, just now, HA versus Q, you have this curve, this shape. So on the, just now we have a system curve. So we will have, on this graph, HA versus Q versus N. So what you do is that the first one you plot the system curve. System curve. So system curve always look like this shape, because HA will be Q square something. So it will look like that. So it's called system curve. You plot on this graph, and then you make full use of the graph. So after you plot the graph, then the next line you look at is the efficiency line. After this one, second, you look at efficiency line, which is always in this shape. All right, this line. You see this line, the red color line, efficiency curve. So efficiency curve always have a peak line, have the peak line, peak point. Focus on that peak point, drop down. We get our Q. And there's an intersect between your system. So this is the point that we will use. Right, this is the point that we will use in our calculation. And then there's one curve called pump performance curve. This one, pump performance curve, given by the manufacturer of the pump. So there will be one curve. There will be one curve given by the operator or by the supplier of the pump. So you, in this example, it go like this. Okay. So there's a curve will intersect with your system pump. You'll go like that. So you see it intersect at point A. Okay. Right. So this is how we make full use. So first, we look at a graph, and then you plot the system curve. Plot the system curve in this equation, using this equation. All right, by look at the system, the graph in the curvature, and it will always in this shape because it's a Q square. Q square, HA versus Q, and the equation is KQ square. So you get this shape. All right. Then the next one, you look at the efficiency line of performance, efficiency line. With this efficiency line always go up and then go down. So you overlap the graph with the efficiency line. Then you look at the peak number. It is here, peak, and then you drop down, you get the Q. And then the next one, you look at the pump performance curve. Right, pump performance curve. With this one given by the supplier or the manufacturer of the pump. In this case, it will go through a certain point that will intersect with the system curve in this one. Okay, then from there, we look at the actual head, we look at the efficiency of the actual pump that operate in this case in A. You can look at the efficiency of the system that you design. This curve is by the manufacturer, the efficiency curve by the manufacturer. So that what is the difference between these 2 points? The efficiency will drop a little bit. Okay, yeah. Yeah. So this is basically about the selection of pump. Okay. And sometimes this one the pipe friction in the pipe is increased. Sometimes the pipe is very long or something. Then your point will shift from point A to point B, but still is still along the pump performance curve. It will shift from point A to point B because of the pipe friction. Okay. All right. So example, this one is in your handout, question 13. We look at two type of system here. So the one on the left, you can see the orientation of the pump, which is in series. So pump continue with another pump. The right hand side graph is a parallel pump, which is both pump in a parallel diagram or parallel pipe. Okay, it will be like your circuit diagram. So you can see here, the first one, you use a head versus Q. You plot the system curve with the equation just now. And then one pump and two pump. This is the pump performance curve, the solid blue line. So if you have a parallel one, if you turn on one pump, and then this one you let it flow free. If you only use one pump, the pump performance curve will look like that. And then if you turn on, you use two pump, the curve will shift up and then move down again. So you have point A to point B. And then for the parallel, you can see parallel. Again, you plot the system curve with the equation just now. HA versus Q. And if you only turn on one of the pump, you get this line. And you turn on the second pump together with the first one, you'll get the second line here. So the point will shift from point A to point B. Right? Yeah. So from here, you can look at what happened to your HA value. Series and parallel. So the increase of your head, if you use a parallel, will be more than this setting. Because if you compare the differences of HA and the differences of HA between the point A and point B will be different. If you have a two pump system, one you set in the series, one you set in the parallel. So series will give you more actual head in a pump, mean that you're able to push the liquid further with a series. And this one, we have parallel. You're still able to increase, but if you have a parallel, means this one will be better in terms of maintenance. Means if one pump is broken, you still have another pipe and you can do maintenance. This one is very hard to do maintenance because if you want to replace this one, you have to shut the flow and you replace a new pump. So it will affect the operation, the date in your contract. So sometimes time is very important in business. So you need to be smart in choosing the system. Okay. So there's also another example in question 14. Yeah, this one, the example that I have is in imperial unit, which is in feet. So the example, the tutorial that I give you is in English unit. However, the concept is still same, right? So I want you to go through this example also. Question 14, go through the PowerPoint slides. Right, it's just application of what we learned so far. Right, how we use the efficiency curve and all this. All the curves are given in your hands up. Right, you just follow the slides and then try to understand how we solve. Okay, how we solve. Just for your info, question 14 will be considered as one of the area in your coming assessment, in your coming exam. So go have a look. Okay. Right. So okay, let me go through this example. Okay. Let me go through this example. Okay. Right. Let's say you're given a diagram like that. Okay. I will go through this one, and this one was given in imperial unit. So, but however, the concept still there. Because why I choose this example? Because I don't have any efficiency graph in terms of unit SI. So I can only use this example to illustrate what we learned. Okay, so let's say we have a system. We want to pump water from one point to another point. All the KL value is given. The length, total length is given, 200 feet. Diameter is given using pump. The elevation is 10 feet. Right, so the statement go like this. Water was pumped from one to another in an open tank. The pipe diameter given, total length given, minor loss coefficient was given, is 0.02. What else? Friction factor is 0.02, which is your F. A certain centrifugal pump having the performance characteristic shown in the figure. So with this pump, what would be the flow rate between the tank? We need to find the Q. And what is the choice from the diagram? Okay, so the first, we pull out the HA versus Q just now, that what we discussed. All right, so we will use this diagram. All right, okay. So how do we solve? The first thing, we consider energy equation. Right, so call out this energy equation: pressure, velocity, elevation, and actual head. Right hand side also same, but the point 2, because why we put our friction component on the right hand side? Because you're sucking water from point 1 to point 2. So your water go through a series of friction effect. That's why we add in the friction effect on the right hand side and not right hand side. And the water is flow from here, point 1 to point 2. So you need to be clever looking at the diagram. What happened if I flip the system? If I flip the system, I have a pump. I flip the system. I pump water from 1 to 2. Okay, what happened? Okay, so you need to be careful. Be careful. Right, in this case, we look at 1 to 2. So your friction is because it go through a series of process, and this is your minor loss. Minor loss of a KLV squared over 2G. And the next step is just a simplification. Pressure at point 1 and point 2 is 0. Why? Because these two exposed to atmospheric. Exposed to atmospheric. P ATM at point 2 and point 1. That's why we can write P1 and P2 equal to 0. Velocity at 1 and 2 equal to 0 because we have an open surface with a big tank. Because it's big, so the drop of surface means the velocity at point 1, drop of the surface line is very, very small. Same with number 2. The raise of your surface level of your water raise very, very small because this is a very big tank. That's why we can use pressure equal to 0, velocity equal to 0 at 2 points. And the elevation here, there's an elevation effect here. Delta Z, where you put Z2 minus Z1, we have 10 feet. Friction factor is given. If not given, you need to read from the Moody chart. F from the Moody chart by using Reynolds number and using Reynolds number versus the relative roughness in the Moody chart. Okay, so Moody chart give you F value, or in the Moody table also, there's a Moody table. Okay. All right, so we use this equation to solve. Again, cancel all the parameter. So at the end, you only have this simple equation. Substitute all the value, right? I just do the mathematics for you. You just substitute all the value. You'll get your equation in this form, in the equation form, which is you have your HA and Q2. So you see the equation HA versus this one. This is your system curve. All right, system curve. All right. So the differences between these two equations is the unit inside the equation. This equation is in feet cube per second. However, because the graph we get from the supplier is in gallon per minute, okay, you need to change this equation in feet per second cube per second. You need to change from imperial unit to gallon per minute. So there's a conversion, right? There's a conversion. After that, you go to the graph. Okay, you go to the graph. So go to the graph. Go to the graph, and then because our graph is HA feet versus Q in gallon per minute, that's why we changed our HA system curve in the gallon per minute. Then we plot, we overlap this equation, we build this line. This is your system curve from the equation, this one. Right on the head versus efficiency, these two lines given by the supplier or from the manufacturer, you overlap this equation on the graph, you draw this one. So so on the hand side here, this line is same lah, is from here lah. So it's here. We just remove this one so that we can discuss more clearly. This efficiency line is actually this line. So there's an overlap of point here from the head performance by the manufacturer. So we extend this point up. You read the efficiency on the left. You know that efficiency is on the left. So you read the graph, you will get the efficiency at the operating point when your system mid operate will be operate at 84%. Meaning your system that you design with this equation, it will operate at 84% efficiency. Straight from the graph. Straight from the graph, you know that the efficiency of your pump already. Yeah. Then you project down. You project down from the intersection point within the manufacturer value and your system curve. You drop down, you know that your pump is delivering at the Q value of 1600 gallon per minute. Okay, this is how you select pump. This is how you select pump. This is how you select pump. Okay. Yeah. And the power, you calculate power from this equation. Capital W dot shaft, you use this equation, substitute all the value you get. The efficiency value 0.84 because from the graph we get just now. Our efficiency is at 84%. You convert when you want to use in the equation, you use 100% is 1. Efficiency is 1. But when our value from the graph is 84%, then we convert our efficiency into 0.84. The rest, you just substitute the value accordingly. At the end, you get in terms of horsepower. Again, this one is a imperial unit example. Okay. All right. So another one is just selection. Selection from between, because we have a question asks us about (18 feet, 100 feet). Oh, so this is just to see what happened to the efficiency and all this. So here you will have 80 feet. Then you have 500 gallon. This asks you the flow rate. Oh. This 80 feet. Oh, okay. Just now, this graph, our HA versus Q square is our system curve. All right. This is our system curve. However, we can plot another graph by changing our delta Z to 80 feet and 100 feet. You can change the what happens if you change the Z here in our equation, HA here. This equation, you change the elevation. Just now is 10. So what happens if you change the elevation, the 10 feet here? You move your tank up to 100 feet or 80 feet. You can bring down. So we are changing the delta Z here. So what happens if I bring my tank lower? So meaning our delta Z will be negative. So this equation can calculate this curve. This one. Okay, so this is the first system curve that we plot, and then we change the equation by changing the delta Z to 80 feet and 100 feet. So we get the second system line, system curve. So this line is your system curve number 2. This is your system curve number 3. So this is system curve number 1. This is system curve number 1 with the delta Z equal to 10 feet. Then this one is 80 feet, 100 feet. So you can see this pump, okay, how do I know that my system can use or cannot use? Because from this is your pump, and you have 2 points. Let me see. This is your tank number 1. This is your tank number 2. So the difference of your Z is here. Okay, delta Z is here, 10 feet. So what happens if you increase the difference between the two tanks? Meaning you increase the delta Z. Original this line is 10 feet. What happens if you increase? Do you move your tank a bit higher, or you need to transfer water to a higher elevation, like a mountain, right? You need to transfer your oil and gas, right? Your oil or gas from a ship and then move to a factory on the mountain. So what happened to your equation? So the first one is 10 feet only. So we look at 10 feet, we have this line. So what happened if you move the tank in second scenario? We move to tank 8 here. Tank 2. Now our delta Z now is 80 feet. Then you do the calculation. Delta Z, you get the system curve with the HA equation. Right? Then you plot inside, intersect with this curve. You get system 2. You see what happened to the intersection point? It is the efficiency dropped to 36%. If you increase the pump from 10 feet to 80 feet, are you able to see what you're trying to do? Our pump at 10 feet will give you efficiency of 84%. But if you pull your tank a bit higher in the mountain, you your delta Z now you change to 80 feet, and you plot this system curve inside the pump graph, you'll see it will overlap in the head curve here. System curve number 2 will overlap here. You drop down, you get 36% efficiency, meaning your pump is dropping. The efficiency is dropping. And then you further increase the elevation to 100 feet. You plot the graph. You'll see the graph here. The graph will not interact with the pump head coefficient, the pump head design curve. Meaning at 100 feet, the pump doesn't work anymore. Because it do not intersect, the pump do not operate. Do you understand what I'm trying to do? Yeah. So the first one, we assume the design system at 10 feet. Yes, it's overlap with the system headline. We get from this intersection point, we extend up. We want to see what is the efficiency at this setting at 10 feet. We get 84%, which is quite good. But what happens if we increase the elevation of a tank? Let's say in this example, we give you example, you increase the position of the tank to 80 feet and you plot the line 80 feet here. And there's an intersection point with the system head here. So from the intersection point, you drop down to intersect with the efficiency line, you get only 36%. So by increasing from 10 feet to 80 feet, the efficiency from 84% dropped to 36%. Okay, so it's quite a high dropping of the efficiency. And if you further increase, let's say you want to transfer water from point A to point B, that higher, the elevation is higher than, let's say, 80, maybe 85, 88 here. Here give you 80, this one is 90. If you design a system to transfer A to point B more than your pump doesn't work. There's no water received at the receiving station. You understand on this graph? Any question? Any question on selecting a pump?
Perfect.
Okay, yeah, I think I explained it very clearly. All right. Okay. So it just explain why it doesn't work if you elevation more than 80 feet or 80 or more than 90 feet lah. Okay, yeah. All right. So these are the practical engineer, design engineer, how they make full use of the curve. So again, just to summarize, what we usually do in pump selection, we look at HA versus Q and efficiency graph. So this one we get from supplier. What we normally do is we get from supplier. And for supplier on this graph, we already have the HA curve. We already have the efficiency curve. So from this one, the next step, you get from supplier or your system curve, we call it system curve, with the HA equal to something plus KQ squared. This equation, you calculate, then you go into the graph, you plot the overlap line, for example. Okay, this one, we know that if we plot HA versus Q, we always get this kind of pattern. So you go to curve, you will get system curve. Okay, you get the system curve. So from system curve, there's an overlapping of 1 point between the HA, between the supplier or the pump tested value. The next point, the third point, you find the efficiency. How you find? You draw a straight line. You look up. There's a point here. You move to the right. You get the efficiency point. Normally, this one will tell you. So this is maybe 90%. So this one is about 80. So you get the efficiency. After that, from the curve itself, you move down. You get your Q, which means your pump will deliver how many water. This one is the flow rate, how many water from the system that you design. Because the system you design is on the elevation of the pump, elevator between the tank. Okay, right? And then, yeah, then from there you try to how do you shift your curve, your HA curve to make the optimum. Right? At what location or what is the elevation will give you the maximum performance. Normally, how you get the best curve? You go back to the this one. You go back to this equation. No, you go back to you go back to this equation. This one. Normally, we try to reduce the system, and we try to reduce the friction, and yeah, okay, reduce the KL value minor. This is the friction parameter or friction, right? Yeah. So this one is a minor loss. This is a major loss. So we have major, minor. Okay. Yeah. Okay. So I think let me look at the time. Okay, I think we stop at question 14. Let me stop the recording.